now we can look at what we have. If we have three different substituents, so we might imagine this is another boron compound, something like BFClBr. So now we have three different substituents, and we want to see what symmetries are still available. So we can put our spin to the center of our triangles, and then we want to see which rotational operations we might still have. So let's see if we have C3 anymore. So we try to rotate counterclockwise by a third of a turn, keep the bottom steady, move the top. If we move by a third, we see, oh, now all of them have changed. So we see that C3 is not a symmetry operation of this particular group. We try C3 minus 1, try to rotate by a third of a turn. So now we want to rotate by a third of a turn clockwise, and we see that again, none of them line up. So we see that C3 and C3 minus 1 are not symmetry operations of the group. We can also try to see if there's a C2 anywhere. So if we want to figure out a C2, we can see if there's one along this axis, for example. So if we turn this way, the green has stayed the same, but orange has turned into pink, pink has turned into orange. Now if we turn it again, we see that this pink one is going to turn into orange. So we see that now we have orange over there. So since all of the atoms have not stayed the same, that means that C2 is not a symmetry operation of this group. So it doesn't have C2, it doesn't have C3. Let's see if it has a mirror plane. So a mirror plane would be along these angles here. So let's see. Well, if we fold it in half, I'm not going to fold this one in half, but if we did, we would see that the orange would go with green. That's not going to work. And again, we can try it with a actual mirror, and we can see that if we do mirror it, we would get orange to orange back there, but it's supposed to be green. So since that doesn't line up exactly, each atom isn't identical, that means that this does not have a mirror plane we call a so-called vertical mirror plane. Now it does have one type of mirror, and this mirror actually goes in between basically in the same plane as the plane of the molecule. So it would go through the boron and the three halogens. So this particular mirror plane is special. And the reason why it's special is because it's what we call a so-called horizontal mirror plane. Horizontal mirror planes are perpendicular to the high-order rotation axis. So if you have a high-order rotation axis, we call a horizontal mirror. Now in this particular case, there is no high-order rotation axis. So for the highest order rotation axis, it's what we call C1. Essentially nothing happens, identity operation. So, but it does have the mirror, and that's the only thing it has. So this is a very special point group called CS. The S stands for Spiegel, which is the German word for mirror. So you will find that in group theory and chemistry, you will improve your German quite a bit. So Spiegel, Der Spiegel is the name of a very important German news magazine, and Spiegel is mirror, and there is only, the only symmetry operation of this group is the mirror plus the identity operation. So let's just talk about the identity operation just for a second. It's sometimes thought of as C1, and the reason why we can always think of it as C1 is if we take any molecule and we rotate it by 360 degrees. Rotate it by 360 degrees, no matter what molecule you pick, no matter which one it is, rotate it by one whole full turn. Okay? Rotate complete by one full turn. Yes, it lines up to where it was before. So this can be called C1, but it's also given its own special name. It's called E, and E again stands for a German word Einheit, and Einheit means identity. We often forget about this symmetry operation. I like to call E the Rodney Dangerfield of symmetry operations because it doesn't get any respect. But it's very important for the group structure, because as you recall, in a group, you need to have an identity element. And the identity element for any group is going to be the E operation. So it's an essential part of group structure to have this kind of operation, even if it seems somewhat trivial. So we've seen that for the planar triangle, we can start with D3H, and then we can lower symmetry to C2V, and then finally to CS. And for our next, so this is the end of episode 2. In episode 3, we will start to look at the point groups of the square. And again, we will start off from the most symmetric form, and then slowly but surely change the substitution patterns and lower the symmetry and see which point groups we would find, and if we can demonstrate the individual symmetry operations of each group. Next time, episode 3, have a go.